Alright, so today I'll be teaching question 2 from the 1989 Calculus AB AP exam, and this is going to be my senior project. And this question reads as, let R be the region in the first quadrant enclosed by the graph of y equals the square root of 6x plus 4, and the line y equals 2x and the y-axis. So then the things that you have to do are find the area of R, set up but do not integrate an integral expression in terms of single variable for the volume of the solid generated when R is revolved around the x-axis, and set up but do not integrate an integral expression in terms of a single variable for the volume of the solid generated when R is revolved around the y-axis. So it's a pretty simple problem. The most work you have to do is for the first part, A, which is you're finding the area enclosed by the region between the two curves. And let's start. So first we're going to start with A. So first you have to figure out which two curves you're using. And the two curves that they gave you, we're ignoring the y-axis because that's obvious. So the curve is y equals the square root of 6x plus 4 and y equals 2x. Now, to better picture this type of problem, although it's not necessary, it's always helpful to kind of sketch out a graph to see exactly what you're trying to find the area of. It always helped me, and it's a good tip to always use. So on the side here, I'm going to draw a graph. So the square root of 6x plus 4 is going to look around like this, and I know that 2x will look something like this. So obviously that's a pretty bad picture, but you know, this is just for my own help. And seeing this picture, we know that it's enclosed by the y-axis and those two curves, so the area R is going to be this area right here. And that's the area that we're going to be trying to find in the first part of this question. So now moving on. So you have to integrate to find area, and in order to integrate you have to find the limits that you're using for the integral. To find the two limits, you have to set both of the curves that you're going to be using to find the area equal to each other. So being that the two curves are the square root of 6x plus 4 and 2x, you set those two to each other. So now that those two are equal, you just plug and chuck, as Mr. Lakaitis would like to say, and get your answer as to where it is equal to 0, or where would x be equal to 0, or where the two curves here would intersect each other on the graph. And here we go. Now, being that this is a video, I'm not going to be asking you if I'm going too fast for you. You can simply pause and rewind if you need any kind of explanation or self-explanation as to what I just did. So now that we see this, although I do not know if this is on the calculator part of the written response test or not, I'm still going to use it just to simplify my life. Obviously, we should be able to do this, being that we're calculus students, but just to make this video a little quicker, it's easier to just plug that into your calculator and work through it and find the two zeros. So what I've already done is I've already plugged them in, and you can look at the graph. So we don't care about this because we know that our y-axis is going to be part of the things that are blocking off our curve and the area that we have to find. So now the only other thing we need to find is a positive x value that would be intersecting. And as we can see here, it's happening right here. Now you can do this in two ways to find what that value is that we'll be using as one of our integral limits. First thing that you can do is you can find the 0 by using second calc and then 0. So now it's going to ask for left bound. And then right bound. And as you can see here, it says x equals 2. That's one of them. Another way that you could do, which may be a little harder, is you go to second and then table, and then look through until you get to when x equals 0, or when y equals 0, what does x equal? Which would also be 2. So now knowing that, we can return back to our problem, and we know that x will equal to 2. Obviously there's another value, but we don't care about that because it's negative, and our y-axis is blocking us off from using negative values in our integral. Now knowing this, we can start to write our integral that we'll be using to find the area enclosed by the two curves. So the integral, start with a sign, will go from 0, because of the y-axis being one of the limits, to 2, which is what we just found, where the two curves intersect with each other. Then when you're putting in the equations of the two curves, you always use the equation that was on top, and then subtract that from the equation that was on the bottom. So if we go back to the slide, where we drew our little graph that was to help us, you can clearly see that the graph of the square root of 6x plus 4 is on top of the graph that is 2x. Knowing this, we can write our integral, which just disappeared. There it is. So knowing this, we can write our integral. Now you always got to remember to write a dx, because everything is in terms of x, so you know you're taking the integral with respect to x. They're really stingy about that on the AP exam. So now we just integrate. Now I do have the answer in hand, but just for you I'm going to do this out by hand, just so you can see how this works out. So first thing you do is, it's kind of hard to integrate the square root of 6x plus 4 just plainly. So what I would prefer doing is replacing 6x plus 4 with a u. So this is how it looks. So then with u substitution, you take the derivative of u. You make it equal to dx. And now you can substitute. And what we get now, if you notice, I still have the 2x there, but I'm not very worried about that, because we know that the antiderivative of 2x is just x squared. And that's simple enough, and I don't need to simplify anything there. So now to take the antiderivative of the square root of u, it is actually u to the 1/2. And then to bring that back, you have to make it u to the 3/2 of 2 over 3. Now, in conclusion, what this is going to look like is like this. So just if you're wondering where the 6x plus 4 came back from, is that if we go back, when we did the u substitution, we substituted u for 6x plus 4. So when we get here to the 2/3 u to the 3/2, you just take the u and plug back in the 6x plus 4. So now with this, once again, as Mr. Lakaitis likes to say, we plug in shock. And we plug in the 2 first, and then we plug in the 0. And you know, you plug in the 2 first, you run it through, and then you subtract what you get there with whatever you get when you run the 0 through. Now, as much as I would love to do this step by step and plug in 2 and work it through and find out what 16 to the 3/2 is. I'm just going to make this quick, and when you run it through, which all of you can do on your calculator since we've used this already, is it's going to end up being this. So that's going to be the answer when you plug in 2 to the integral we got up here. Then you subtract that from whatever you get with 0. And when you plug in 0, we get 8/9. So this is what happens when you run the 2 through and then subtract it with what you get when you run the 0 through. Now the answer to this is going to be 29s. I'm not going to run step by step as to how I got 29s, because all of us should be able to transform what we got before into fraction, subtract again, and you get the answer. It's fairly simple. This is our answer to A. Now, I do not know the point values for this, but with that answer and with all the work that we just did, you're getting all the credit for part A. So now we're going to move on to part B. Part B is a lot simpler than what we just did, because in part B we're just finding the volume of what the area that we have just found when it's revolved around the x-axis. So now once again it's a lot easier if we have kind of like a graph to show us what we're doing. So here's the graph. And once again I'm going to shade in the area. So the pink should be able to show up on this video, so you can clearly see what we're revolving. Now, you know that this is 2 over here, and this is 0, and in part B, it's asking us to write an integral without solving it for the revolving r around the x-axis. Now, what that is well, we're revolving. That's my point. I don't know what I was going to say. So now we're going to write the integral. So when you're revolving, as you've learned before, because it's around the x-axis, you're using once again the same 2 limits. So from 0 to 2. Then you know that it's pi r squared, and this is going to be our radius. And the pi comes out because I forgot what it's called, but I'm something like a constant, so it's pi. Now I find this weird, what it says on the solution, so I'm going to do it the way this was taught in class. This is going to be a washer. I can tell that for sure, because we're going to have a big hole. So for washers, see, I think I'm making a mistake now. I'm going to write down the answer so you'll be able to see, because the answer is just the integral. And what it's going to look like is this. So pi times the integral from 0 to 2 of 6x plus 4 minus 4x squared. Now what should be happening is it should be the top radius squared minus the bottom for the top curve equation, or radius types. So the way this works is pretty much what you're doing is when you're revolving, you're going to be revolving this whole thing around the x-axis. So because we have the y-axis as one of our constraints, we know the two is intersect, so we're only revolving this part right here, this little bit. So when we're revolving this around, what you're doing is you're kind of revolving this whole equation, the equation of the square root of 6x plus 4, first around, and then we subtract that from the revolution of this 2x, because this 2x is making that whole, I'm hopefully not confusing you all, but what it would actually be is the square root of 6x plus 4 squared minus 2x squared, because you're doing pretty much your top equation squared minus your bottom equation squared, because it's pi r squared. Now, the reason I was confused before is because the way the answer is written here is already simplified. So because we square the square root of 6x plus 4, the square root goes away, and 2x squared is 4x squared. And that's the answer to B. It's quite simple. I may have complicated a little, but it's actually very simple, and I don't know why I complicated this for you all. So now we're going to move on to part C, and with this answer, you would get full credit for part B, and it's all good. So now we're moving on to part C. Now, although part C is not as difficult, it's still pretty difficult, just because we're now revolving the volume around the y-axis. So pretty much we're doing what we did in part B, except now instead of looking at the graph like we just did, so our graph right here, this little graph with this area being revolved like this, now it's being revolved around the y-axis. So now there are two ways to do this. One way is you pretty much have to split up the equation, which I think is a lot more difficult to split it up. So first I'm going to write the answer, and then we're going to work backwards, just like we did in the previous problem, because I keep getting confused when I don't do it this way. So the answer they give is the volume, when revolved around the y-axis, is going to be 2 pi on the integral from 0 to 2 of the square root of 6x plus 4 minus 2x dx. Now that's the harder one, because usually when you're revolving around the y-axis, you want to change everything in terms of y and work through that way. So it is really strange that they did it in terms of x. Mr. Lakaitis never taught us this method, so even though this is one of the answers, I would avoid this. So now I'm going to give the answer that I would personally prefer to do. So you may notice that this is two different integrals, and that's because you're subtracting from 0 to 4, this right here, to 2 to 4, which I'm assuming would be this right here. So what leaves you is just this, if that makes any sense. So you're taking the whole one from 0 to 4, which would give you, let's see if I can do this with a vivid color. Hopefully this will show up on the video. You're taking this, 0 to 4, and you're revolving it, and then you're subtracting from that this. Or, that's a really bad picture, I'm not going to lie. But you're subtracting. It's a really bad picture. This is bad. So the method, I'm just going to go into explaining to find this, because it's not a washer. It's just going to be pi r squared with only one radius, and you're going to go from 0 to 4. Now 4 is where this intersection happens right here, of pi, and then y over 2 squared dy is because of that. So we took this and we revolved it from 0 to 4. Now, what we subtract is from 2 to 4, so from this point right here, where our square root of 6x plus 4, or the new way, so as you can see, the y squared minus 4 over 6 comes from transferring our square root of 6x plus 4 over in terms of y, and again we're taking in respect to y. So once again we use our pi r squared idea for revolving, so we put the pi out in the front. Our r is going to be the square root of 6x plus 4, or in terms of x, or in terms of y squared minus 4 over 6, and we subtract that revolution, so this revolution right here, from the big one that we've already taken, leaving this area right here, this little bit that we have left, is going to be gone, which leaves us with the exact r that we wanted, and this brings us to the right answer. So that may have been a pretty confusing explanation, and I apologize for that. In my mind, it made a lot of sense. That right there is how you solve the second APB calculus problem from the 1989 exam. If I feel really bad, I might later on post another video explaining a better way to do this, because this I feel is pretty bad, but I also think it's pretty good. So I hope you guys get it and do great on your AP exam if you were doing this before the AP exam. Thank you.